In this video, I'm going to show a brief tutorial on how to use the HY8 software for culvert analysis, go through a couple of examples, and also show you where you can download the software. To download the software, go to the Federal Highways website, and you can see that they've got the version available for download right here.
Let's work through a couple of examples just so that you can figure out what the fields are and how to translate a drawing or some physical circumstances out in the real world to calculations that you'll need to perform in the program. All right. So this is a top view. I made this sketch. It's so nice. You can tell that it's a road because there's the dashed yellow line. I went all in with this drawing. And guess what this blue thing is? It's water. Well done. What I wanted to point out is that the width of the channel is 5 meters. The culvert is going underneath the road to pass that water through so it doesn't go over the top of the road. There are different things, different fields that we can enter into HY8. Some of them don't matter. Some of them you just enter for purposes of reference. For example, it's going to ask about roadway stations. And so roadway stations is a way of saying where you're at in a road. So in this example, let's assume that here a certain spot is 5 plus 0, 0, and then the river begins at 5 plus 3, 5. These are meters. And so the roadway station at the end of the river would be then 5 plus 40. Now, this S0, that's the slope of the river itself. And so the reason why water is going from left to right, just like that red arrow indicates, what's causing the water to move is the fact that the river is downhill. And here's the slope of the river. In HY8, it's going to ask us what's the slope of the downstream channel because it wants to calculate the capacity of this channel. It wants to know how much water can get out of the way of the culvert once it gets underneath the road, because whether the depth of the water downstream is high or low affects how much water can get through the culvert itself. We have a design flow of 25 cubic meters per second, and we expect a maximum flow to go up to 30 cubic meters per second. The channel, the N value is a roughness factor, and the higher the roughness factor, the more energy loss there is as the water goes over a surface. And 0.05 is just maybe typical for a channel that doesn't have a lot of debris or very large stones in the way there. Yes, go ahead.
Should I register the HY?
No, you don't need to register. You can just cancel that. All right. So here's a side view of the same thing, a cross-sectional view. So remember, we've got a road, and what I've done for this next view is cut the road here. And I just want to look at how tall is the road above the channel bottom. And that cross-sectional view will give that to me. So here's the river again. And so the channel has the invert elevation. That means the bottom of the culvert at an elevation of 300 meters. And the top of the road is at 307 meters. How wide is the road? It was a 2-lane road from the previous drawing, but it looks like the roadway width is approximately 20 meters wide. That's a really wide road, isn't it? That's a wide road. What we want to find out in this example is a 24-inch diameter culvert going to be okay? You know, can we get enough water through that culvert if it's 24 inches in diameter so that there's no overtopping? So in other words, we want to get this design flow of 25 cubic meters per second through the culvert, and we want to know if 24-inch diameter is going to be all right. So that's the analysis we're going to do. The outlet elevation here defines the slope of the culvert. So the slope of the culvert can be different from the channel slope, potentially. And in this case, it is. I think that's all we need to look at before we start up the program here. Let's see if we can represent this system in HY8. So what I'm going to do is create a new project and add a culvert crossing. So that's the default options that are selected when you start. What I want to do, though, is I'm going to switch it over to metric, since the dimensions that I've got are in metric. All right, so go into the project here, and I'm going to put in a crossing. All right, so the minimum flow, we'll analyze it starting at 0 cubic meters per second. That's what CMS stands for. Our design flow was 25 cubic meters per second, and we want to look at what's going to happen all the way up to 30 cubic meters per second. All right. Now the channel is talking about the river that is downstream of the culvert. And here, just for simplicity's sake, let's say that it's a rectangular channel, meaning that the let me draw a cross section to show you what that channel looks like. The river has a width of, from our first drawing, 5 meters. So here is the river after the culvert. It's 5 meters wide, and it's a rectangular channel. Most of the time, channels like this would be trapezoidal, but just as a starting point, let's say rectangular. Okay, so the bottom width is 5 meters. Channel slope is this parameter, 0.0025. That's telling you how steep the stream is. 0.0025 meters per meter. So that's 0.0025 meters of vertical drop for every meter of horizontal distance. Okay, so the end value for the channel, it was 0.05, right? That was the roughness. Oh, yeah, 0.05, so that's how rough the river channel bottom is. And the channel invert elevation. Now what that's asking about is it's asking where does the channel match up with the outlet of the culvert. So the value we need to put there, we're talking about what is the channel elevation where it meets the culvert. Now you could have the channel lower than the culvert so that the culvert outlets and then that's actually like the water pouring into the channel. But in this drawing we see that the channel invert matches against the outlet invert. So I'm going to put 299.95 as the channel invert elevation. Okay, so 299.95. We could click here and it would give us a rating curve that says what flow rate you get with which depth of flow. So in our 5 meter wide channel, if we have 4.4 meters of depth, that corresponds to the 30 cubic meters per second. That's the maximum we expect to see. So this just is calculating for, gee whiz purposes if you're interested. One of the kind of cool things is it also calculates the shear stress so that if you know what your channel downstream is made of, you can know if the bed is being suspended by the shear stress for a certain flow rate. So is it going to start washing away a sandy channel when you've got really high flow velocities and so on. All right, so that's the tailwater data. Now, the roadway data, it needs to know that information in case the water gets high enough that it starts flowing over the top of the culvert. Like, consider the worst case scenario. The worst case scenario is that we didn't make our culvert big enough and the water keeps getting deeper and deeper and deeper and then it flows over the top. So if it gets that deep, the computer wants to know how wide is the roadway surface, because how much water can get over that road is going to depend on what's the road made out of, because there's a roughness implied in that, the length of a weir, the width of the obstacle, and so on. So that's sort of why we are defining the geometry of the road, is in case the water overtops the culvert. So let's put that in. The first roadway station, 5 plus 0, 0. Okay, so 500 meters. The crest length is 5 meters wide. So if water is going over the road, then it's going to be acting as a weir with a length of 5 meters. And so I'm putting in the channel width. Now if we had a trapezoidal channel, then it wouldn't be the same as the bottom width. And we'll work another example in a minute where instead of this rectangular, if you have a trapezoidal channel like this, and then like here's our road, then the channel width of 5 meters wouldn't be the same as where the water is going to be flowing over the road. So we need to be careful to define the correct length in case there is overtopping. So here our crest length is 5 meters, and the crest elevation is asking at what elevation is the road. And here it's at 307 meters of elevation. So that tells it how high the water has to get before it starts overtopping. So 307 is what I'm going to put in for the crest elevation. And the roadway surface is paved. And then the top width is 20 meters. That's the distance from here to here. It looks like maybe it's a little less than 20 meters because they put the paving asphalt on top of the road base, but came in a few inches. But essentially 20 meters is what we need to put in here for the, I keep clicking on the wrong thing, top width, 20 meters. All right, so any questions so far? All right. Now, that's all about the crossing. Here are the properties of the culvert that we want to analyze. And the question was, is a 24-inch diameter culvert okay? Well, 20-inch, we need to put that in SI units. If we multiply 24 inches by 25, because there's 25.4 millimeters per inch, 24 times 25, it is about a 600 millimeter culvert diameter that we want to analyze here. All right, so we're going to analyze a 600 millimeter diameter culvert, concrete, circular. There's a lot of different shapes here. You can have a box. Remember we saw that picture from the UAE was like an arch. But ours is circular concrete. Embedment depth is talking about how deep into the base the culvert may be put. The typical, I'll just leave it at the default value of 0. This Manning's N value is determined by the material, so 0.012 is a typical roughness for concrete. So I'll just leave these all with the default options. It doesn't change the performance very much if you change around some of these parameters, like whether it's straight or side tapered. You can play around with it. In fact, I ask you to do that on the homework assignment, to play around with some of these options to see how much it changes the flow conditions, but it doesn't have a huge effect. So we'll just leave it sort of the default options for these things, but we do have to tell it how long is the culvert. So defining the inlet station and elevation, outlet station and elevation, this is critical to get right. So our beginning station is 1 plus 0, 0. Outlet station is 1 plus 20. So I'm going to put that in 100 and 120. So the length of the culvert is 20 meters. Now the inlet elevation and the outlet elevation, back over to here, 300 meters and 299.95. It was 300 and then 299.95. Okay. And one barrel means there's right now one pipe having these characteristics. At a single crossing, we could put in additional pipes and find out what's happening there. So let's click on Analyze Crossing and see what sort of information comes up. So remember, what we wanted to do is we wanted to find out, can we avoid overtopping with a single 24-inch pipe? What this report tells me is that overtopping occurs very, very early. I mean, this culvert is much too small, because I can only get about, remember the top of this is 307. When the water elevation, the headwater is at 307, I'm only getting 2 cubic meters per second through the culvert. And all the rest of the flow has to go over the road. So when I'm at my design flow of 25 cubic meters per second, 2.2 cubic meters per second is going through the pipe, and all the rest of the water is going over the top of the road. So this culvert's too small. So design is an iterative process. It's that optimization process of doing things over and over again until you have a solution that's just barely good enough. You know, the most economical solution is the thing that's just barely good enough to satisfy the objectives. So let's play around with this and see. From the drawing, you can see the headwater is higher than the roadway profile. Let's go back to the parameters of the crossing. Let's see, where can we, yeah. How big would it have to be? Maybe we could put in more barrels. You know, could we put in 5 barrels? What's going to happen there? Analyze it again. So with 5 barrels, things are improved. At 25 cubic meters per second, now we've got 10 cubic meters per second through the pipes and 14 going over the road. So that's less of the flow in the wrong place, but still not good enough. There's a lot of different curves that you can get in the reports here. This is shows you for a headwater elevation how much is getting through the culvert and overtopping. You can export these reports as PDF files if you want to, let's see what we get from that. All right, so the report that it, the report that it gives us is, this first thing is the same table that we saw before, which is headwater elevation versus how much flow is going through the culvert versus how much is going over the roadway. That's not a really detailed report, is it? They've moved things around a little bit. There's some questions I'm going to be asking you. Yeah. There are some questions I'm going to be asking you where I'm basically asking you to find out what is the depth of water at the outlet, what is the critical depth, and so on. So you can get that here through the culvert summary table. And you can find the velocity of flow in the channel after the culvert, the tailwater depth at all of these different flow rates. And for us, 25 cubic meters per second was our design flow rate. And so you can find out how deep is the river downstream of the culvert at that design flow rate. All right, so any questions with this first example?